Today I'll continue with the waveguiding aspects. In the last talk, we discussed what confinement factor was, gamma, and we showed that only a part of the light that is emitted in a slab waveguide is contained in the active region. Now let's look at the perpendicular geometry. Let's look at a three-dimensional view of a laser. Say this is the length of the cavity L. This is the Z direction. Okay, this is the X direction, and this is the Y direction. Okay. Yesterday we were considering propagation in this slab waveguide, in which we have a refractive index here N2, N3, and N1. Okay. We are looking at this geometry. This is the active region. Okay, and this could be called the width of the device, and the substrate here is here. This could be called the depth or the thickness of the device. Okay. So this is the active region. The contacts are taken and current flows like that, and suppose you have a contact here, current flows out. Okay, now in order to have a high current density, we know that the current density J is the current over the area, the active area. And the active area is obviously this W into L. In order to increase the current density, we want to reduce A. And as I've discussed, one of the most common geometries is a stripe geometry. So we have a stripe here. Okay, this is of width S, standing for stripe, and typically S is of the order of, say, 10 microns, whereas the width W can be 120 microns, say. Okay, L it could be 400 microns, and D could be something of the order of about 200 microns. Okay. So this has to be defined by photolithography, and there are various ways of achieving this stripe geometry. So the current only passes through this region. I'll talk about how it's achieved later on, the technology of making stripe geometry lasers, but you can quite understand that by some masking of photolithography steps. Suppose you have an oxide, suppose you have an oxide here, okay, some sort of, okay. So the current, this is an insulator, okay, so current cannot flow, and as a result of this oxide stripe, what happens, the current flow is mainly, okay, and there may be slight, so current flow is like that. Okay, most of the region is outside this streamline, and where is the laser action taking place? It's taking place in this active region, but over. So the aperture from which the laser output is coming is an aperture like that. Okay, and remember, sorry, I should not call this D, because D is this. Okay, maybe this should be called T. Okay, D is the active region thickness, and notice that we take D could be something like 0.2 microns. Okay, so we have a slit, almost a slit like that, D by S, through which the light emerges. This is an edge emitting laser. Okay, this is as opposed to a surface emitting laser. And we are also concerned, we want to look at the effect of the stripe today and see what happens. Of course, the overall current requirement comes down because the area is reduced. I is equal to J into A. So if there's a certain threshold current density, I is equal to J into A. So I threshold is reduced if A is reduced. And remember, it's reduced from 120 to 10 microns. Okay, so factor of 10 or 12. So this is what is known as a stripe geometry, which is very commonly used for all type of structures. And we are interested in the advantages of stripe geometry. We are interested in the light output coming out from this laser. Okay, the light output will obviously be coming from this aperture. And what is the modal pattern? The light output will spread both in this direction, okay, as well as in this direction, both in X and Y direction. So what is the theta? One of the definitions is, okay, this is the plane of the active layer. Okay, so in this plane we define the divergence as theta parallel, okay, and perpendicular to the plane, this is theta perpendicular. Okay, so now from simple physical optics we know that if D is small, okay, then small aperture, the divergence is going to be large, so theta perpendicular, since D is much less than S, theta perpendicular is going to be much larger than theta parallel. So the beam coming out is not going to be sort of circular in cross section. There's going to be much more spreading in this direction, perpendicular to the plane than parallel to the plane. So we are interested in the radiation pattern from this stripe geometry laser. We are interested in the threshold current, and we are interested in the modes, the various transverse electric or transverse magnetic modes that can propagate in this cavity of length L. Remember, this facet is a reflecting facet, reflection coefficient say R1, the other is R2, so the light is bouncing back and forth from these facets, and this facet is obtained first by cleaving and then by some anti-reflection coating if necessary. Okay. For high power lasers, this facet has to be coated with a hard coating so that there's no damage. Remember, the power output coming out could be quite large. Okay, it's a small area. Okay, so what is the advantages of why go for stripe geometry? One is obvious that I've already stated, that we have reduction of the cross section area, so lower ITH. And it's quite important, if you can reduce ITH from 100 milliamps to 10 milliamps, that is of great benefit. Okay, we have another advantage. Effective surface recombination is reduced. Because we do not have current flowing all through the device area. Okay, for example, we don't have current flowing through this surface. It is only centered around the middle of the device. Okay, so the effect of all this surface, which could cause leakage current, is reduced. However, there could be some leakage current, and we want to have some methods of reducing it further. And this also gives increased reliability. Because after all, there's a PN junction, because the PN junction has lower leakage current. Okay, these are two obvious advantages. Another advantage is the corollary of lower area, lower capacitance, lower device capacitance. So you have lower RC time constant. So this is one contributor to the temporal response. So you have higher speed. And remember, reduction of an area by a factor of 10 will obviously reduce the device capacitance and increase the speed. The fourth advantage is that it follows from the cross-section. Okay. Now if we draw the end-on cross-section of the device, okay, say this is the active layer thickness, and this is the stripe geometry. This is minus S by 2 and plus S by 2. And this is the middle of the device. Okay. This is now the Y direction. Okay. And this is the X direction. And Z direction is. So the light is coming out perpendicular. And if this is the stripe geometry, then, and this is the active layer, of width and thickness D, reduction of the total length from W to S, which is of the order of 10 microns, obviously means that this is the active layer width. That means there is much stronger probability of getting single mode operation. Okay, so fundamental mode operation. And I talked about different lateral modes last time. So you will probably, it is more easy to get one single fundamental mode. The electric field of that could be, something like this. Okay. Fundamental mode operation is more likely. On the other hand, filament formation and multi-mode operation is less likely. A laser is an active and reasonably high current density, high power device. So in all such devices, you have the possibility that when you have a large area like this, suppose you take a broad area, as opposed to a stripe geometry laser, you have what is known as a broad area laser. Okay. This is okay for device testing. Suppose you don't make a stripe geometry, you make a contact right there, okay, and you pass a current. What are the disadvantages? Disadvantages is obviously there's a PN junction here somewhere, okay. So the PN junction, there may be some leakage current around the periphery, okay. There may be breakdown, additional leakage at the junction of high electric field. And if you're passing a high current, what may happen? That due to material defects or due to geometrical delineation, you may get filament formation, meaning that there may be regions, the whole current will not be uniformly distributed, but you may get, okay, the current density here will be much higher than right through the sample. Okay, so this means that this region may laze much stronger than these regions. Okay, so this non-uniformity of current flow, this happens not only in lasers but in all high power, in rectifiers, high power, high current rectifiers, that you have this possibility of filament formation, and this could be destructive. Okay, you're passing a small current, but in this region, if the current density is very, very large, you get a lot of heating, and filament formation leads to destruction of the device. It's a thermal effect, which has to be overcome in many high power devices. Okay, so this filament formation is also undesirable, and it's overcome by using stripe geometry. Okay, this broad area laser which I have drawn could be used for things like for just testing a device. Okay, just testing a device. Say pulsed testing. Of a laser diode. But the actual devices are always stripe geometry, and so let's come back to a typical stripe geometry. Minus S by 2, 0 plus S by 2. S, I gave you a particular figure. It could be something like 5 to 30 microns, depending upon the masks available. This is X, this is Y, and this is Z. And we want to look at the modal intensity. Okay, what is the intensity? How does the intensity vary across Y? Okay, is it Gaussian? What is the distribution? How does the intensity of the light vary with Y? And what are the conditions that give you single mode operation? So obviously, again, we are interested in looking at the electromagnetic fields in this configuration and the way the electromagnetic wave propagates. And so we have to look at the wave equation. looking at the electric field distribution in this direction, delta 2 Ey plus K0 squared epsilon by epsilon 0. Epsilon is the dielectric constant of the medium. Epsilon y is equal to 0. Okay. Where K0 is the free space 2 pi by lambda. Okay. Now the E field in the y direction, that is perpendicular to the these are the junction plane, perpendicular to the junction. Sorry, this is parallel to the junction plane. Okay, this is parallel to the junction plane. Is strongly influenced by spatial variation of epsilon. This epsilon is not uniform, it is of epsilon in the y direction. Remember, a passive medium has a particular dielectric constant, okay? But this is not a passive medium where you're getting injection of electrons and holes. So obviously the dielectric constant is changing, and if the electric field is varying, the injection current is varying, the electron hole concentration is varying, and then the dielectric constant will also vary in this. So you have a dielectric constant, the function of x and y, which you can, that's the relative dielectric constant. We can say that it may have a variation, a parabolic variation of this type. A squared y squared within the active layer. And this is equal to, in the boundary layer and the barrier layer, there are no carriers, and then we say that it is just the dielectric constant of the barrier. Okay. At y is equal to 0, at the center of the stripe, we can say that the complex dielectric constant epsilon 0 is equal to, there's a real part and an imaginary part. This is giving the loss, and the A constant here, A, the complex, that also has a real part and an imaginary part. Okay. So with these inputs, we want to solve the wave equation, and an approximate solution we can use separation of variables method is Ex x y z is Ey x Ey y exponential minus j beta z z. Z is a propagation direction. Now we assume that the epsilon, the dielectric constant, varies slowly with y in the junction plane. And Eyx is not significantly affected by by the confinement. So separation of variable, we have assumed that Ex is product of Eyx and Eyy, so we get the equation del 2 Eyx del x squared plus beta x squared Eyx is equal to 0. Okay. Substituting this assumed solution, substituting this into this and simplifying, we get a fairly large expression. Just to show that it is possible, you can work it out. You get d2y delta y delta y squared plus k0 squared gamma. The confinement factor is coming in, epsilon 0. This is at x equal to 0, and epsilon 0 is a free space, plus 1 minus gamma epsilon 1 by epsilon 0. This is significant. This type of variation we will come across later. Within the active region, we have epsilon gamma. This is, and outside the active region, there's 1 minus gamma into E1. So in the case of multi-quantum well, quantum well lasers, then we'll find out that within the active region it's gamma into epsilon, and outside the active region it's 1 minus gamma into epsilon 1. And the other terms, minus beta x squared minus beta z squared minus gamma k0 squared a squared y squared by epsilon 0 Ey is equal to 0. So this is the final sort of field distribution, variation of y, Ey, the electric field in the y direction. We can look for solutions of this expression, and the fundamental mode, the solutions are Hermite polynomials. French it's called Hermite polynomials, and we're interested in only the fundamental modes. So Eyy is HP, the Hermite polynomial of pth order, gamma to the power half, a k0 to the power e0 to the power half. Y into exponential minus half gamma by epsilon 0 a k0y squared, where this is the Hermite polynomial of order p. Hp xi by definition is minus 1 to the power p exponential xi squared delta p exponential minus xi squared over delta xi to the power p. This is the basic definition of a Hermite polynomial. You could just check that this relation is correct, all the terms are there. If you're looking for the first order, it turns out that H0 xi is just 1. If you put p equal to 0, then it's just 1. H1 xi, the argument is xi, is just twice xi. H2 xi is just 4 xi squared minus 2. So these are the ones that we are interested in. And so if we put P is equal to 0 for the fundamental mode, and the intensity is proportional to the square of the electric field, so fundamental mode intensity EY, the magnitude squared, variation along the y direction, turns out to be exponential minus gamma by epsilon 0 to the power half AR K O Y squared. So this is exponential minus something squared, so this is a typical Gaussian distribution as a function of y. Notice that this AR influences the intensity distribution. Along y, because after all AR is very along y. Okay, I won't go into writing the expressions for all the other higher order modes, but this Gaussian distribution tells you that for this mode the intensity variation will be something like that, okay, in the y direction. This is in the far field. And if you look at the actual aperture, this is the aperture through which the light is coming out perpendicularly. Okay, this is this S is 10 microns. Okay, if this is 10 microns, then what you'll find in the case of a single mode, there'll be a single maximum here, which is characteristic of a single. This is the maximum intensity, okay, and the intensity will decrease. And this is what you want for the fundamental mode of operation. Okay. Suppose S is not so small. Suppose S is. What are the dangers of taking higher values of S? Suppose S is, say, 20 microns. Okay. Then it is possible that you will get a higher order mode occurring. In the higher order mode, the intensity will be described as Hermite-Gaussian, and it will be something like this. Okay. And the light output could be corresponding to this. And there is no very low intensity on the axis. Still further higher order, these are lateral modes, okay. As opposed to different longitudinal modes. The length of the cavity determines different longitudinal modes. These are different lateral modes due to the width of the finite width of the stripe. You could get for SE, you could get a mode of this type. Okay. So in this case, you would have. So the conclusion is that as S is increased, you have more higher order modes. And the intensities here are given by the Hermite function. They're called Hermite-Gaussian intensity. In fact, if you look at this, suppose you are using this for optical fiber coupling. The fiber is here in the center. This is completely useless. Okay, the light will not be entering the fiber at all. However, if you want to use it for some other just illumination, okay, fine, you get a broad beam, it may be okay. But otherwise, you're not getting the light intensity at the maximum of the exiting waveguide. So, I hope this explains the importance of the stripe geometry. Now, if we come to, okay, I think I have a few graphs here. I don't know if I showed this. Okay, this, if you can see, this is a broad area laser. Okay, I don't know if I showed this earlier. So you have a overall area contacts back and front. Okay, so this is double heterojunction indium gallium arsenide phosphide. You have a high threshold currents, large heating. Okay, but it can be used for quick pulsed characterization, whether the light is coming out, whether it's lasing or not. Okay, and a typical stripe geometry laser is something like this. Okay, here's the stripe. Here's the active region where the light comes out. This is a total bottom contact is N-type as a metal. Here you have a limited area. And how do you define this? Well, you can have an oxide stripe. Okay, this is called an oxide. You have an oxide, and here you don't have an oxide. Okay, so and you metallize. Okay, so the metal makes contact only to this region. Okay. You can have proton isolated lasers. That means that if you make a mask, you bombard this area with proton. If you bombard it with proton, this area becomes high resistivity. Okay, so you can have a thing called, this used to be done earlier, but nowadays it's not. You don't want to have another proton beam, so you make the laser structure. Okay, you put a metal mask, and then you bombard with protons all over. Okay, so protons will damage this region. Okay, so this becomes high resistivity. So again, you have the current will only flow that direction. Okay. These were in the first years of laser fabrication, but more recently, you can use junction isolation. Okay, and I'm not sure whether you can see this. This is oxide stripe laser. Okay, you have an oxide. Here, this is a p-n junction isolation. Okay, so here you have a p plus. This is the active region. Okay, and here you have the p-n junction, which is reverse biased. So this is by multiple growth. You grow this central area first, then you etch out. Okay, and then you grow this, and these layers are back biased. Okay, so here you have PN, so this is called PN junction isolation. So you have N and N P indium phosphide, PN junction. This is called an etched mesa buried heterostructure, EMBH, EMBH type of structure. Okay. Let me just finish by talking about the far field patterns. I think what is the light intensity coming out of a device? Okay, looking at this. Okay, so what is the light intensity coming out of the device? If we just sketch Okay, this is the little thin aperture from which the light is coming out, and if I draw this, okay, light is coming out in a sort of a cone, and if you look at the divergence, okay, here it is so we have, and okay, so this is the x, this is z, and this is y direction, and as I've defined, this angle is theta perpendicular, because the plane, this is the direction of the plane, and this angle is theta parallel. Okay. Now, we've seen that S is of the order of 10 microns, and D is of the order of, say, 0.2 microns. So, just due to diffraction from this aperture, we find that theta perpendicular is of the order of 35 to 65 degrees, which is quite large. Okay. Remember, the wavelength of light we're talking about is, 1 micron. Okay, so there is very strong diffraction from this little aperture, and theta parallel is of the order of about 10 degrees. Okay. So the divergence is quite large, and it's found that I'll get into the actual expressions for this next time. We'll find that obviously the intensities depend upon, we want to look at I theta, how I theta over I0. Okay, I0 is on axis. As theta changes, how does that vary? And this will be obviously equal to, we look at E theta squared over E0 squared. Okay, we will look at the expression for this, which follows from the far field field intensities. It turns out that, for example, if you want to look at theta perpendicular as a function of D, this is the full beam between the half power points. Okay, so if the intensity here, the intensity here will suppose go something like, okay, in this plane. So this is, we define the half power points. Okay, that will be the theta half power points. It turns out that there is an optimum value of D here. You find that, okay, you get variations like that. The dotted lines are where, if you have higher values of D, you have possibility of higher order modes. Possible. And there is a, okay, for, we do not want high value of theta. Okay, we want a low value of theta, so we should stay somewhere here for low values of D. You get low values of theta. So we do not want this maximum. However, what are these graphs? These are for different values of x. This is x equal to 0.6, 0.5, and this is equal to, x is equal to 0.1. Okay, so we see that, again, this is for a AlGas structure, aluminium X, gallium 1 minus X arsenide. okay, where the two important parameters here determining theta parallel, theta perpendicular are obviously x and the width of the active layer. So I'll continue with this discussion next lecture.